skip the steps. So it's important that you do not skip the steps. Why? Because you might put oxygen at the center instead of carbon. If you do not skip steps, you will always get the right structure. As you get better with drawing them, you will remember the rules and become a champ at drawing them. Well, let's go team. Multiple bonds then. So what are the Lewis structures? Do some paper then with the models. So you can get chemical models probably on various online shopping websites. Used to be able to buy them from the chemistry department, but that's not happening right now, I don't think. So what are the Lewis structures? Do it on paper, then use the models. So C2H3Cl, CH2O2, C2H3N, CH5N, C3H6, HCN. Atoms have a tendency to form multiple bonds are the CON, SP, especially carbon, oxygen, nitrogen. Actually, all of them, yeah, you know, they all do. Phosphorus can be the one, well, yeah, there's a lot of phosphorus atoms as well. Okay, I'll just do one of these. I'll do the first one, and then I'll let you do the rest and encourage you to actually do them because the more practice you have with this, the easier it's going to be, at least spotting which one it's going to be. So here we have a C2H3Cl. So I'll start up here. So carbon is in group 4A. There's 2 of those. So that's going to be 8 electrons. Then hydrogen is in group, well, 1A, I guess. It's not really like definitely in group 1A. So it's 3 of those, so times by 3. Oh. And then chlorine is in group 7A. There's only 1 of those. That's only 7 electrons. So we look at this, we have 18 electrons. Okay, next thing is, of course, to draw out our skeleton structure. So carbons are in group 4A, so they're the lowest group except for hydrogen. So we have 2 carbons, and then we have a chlorine that could go on here, like a terminal atom. And then the hydrogen, generally attach it to the, we generally always attach these things to the atoms with the, what do you call this? With the lowest sort of electronegativity or lowest group number. Then I'll put the other 2 here, 1 each on the carbons, just for symmetry purposes. Nature generally likes symmetry. Okay. So that's all of our atoms, right? So 2 carbons, 3 hydrogens, 1 chlorine. All right. So then we have 1, 2, 3, 4, 5 bond pairs. So 5 times 2 is 10. So 10 electrons involved in bonding. So that gives us 8 electrons remaining for lone pairs. So we put those on the chlorine. So okay, because hydrogens don't take it. And then what ends up happening is, have I drawn this the right way? Right, so then we have chlorine has 8, each of the hydrogens have 2. This carbon has only got 6, and so this carbon only has 6. And so that would tell you that there's been a mistake made somewhere. So most likely what should have happened is, according to our Lewis rules, which I didn't use, which you should use because otherwise you'll end up with problems like this. Put the hydrogens here so that then this lone pair can be shared here. And then we can form a Lewis structure that looks like this. But actually what really will happen is this one. HCl C double bond C Cl, and then H, something like that, as opposed to what I just drew. So using formal charge to predict stability. So this is where another part that we need to sort of always be applying to our Lewis structures, because this helps us to understand why certain things, and like this gives us an additional level of knowledge, which will help us to determine which order the atoms go in whenever we make our initial skeleton. So when possible, several Lewis structures are, when several Lewis structures are possible, the most stable structure will be when the atoms have the smallest amount of formal charge. So any negative charge resides on more than one electronegative atom. So what is the formal charge of CH4, methane? So the formal charge, Fc, is equal to the number of valence electrons minus the lone pair electrons plus a half of the bonding electrons. So the formal charge of carbon is 4, which is the lone pair electrons, minus 0 plus a half of the 8, which is the bonding electrons, which is 0. The formal charge of hydrogen is 1, minus 0 plus a half of 2, which is equal to 0. So if I draw out the structure of Lewis structure of methane, so it's CH4. So carbon is group 4A, so it's 4 electrons. We have 4 hydrogens, so that's going to be 4 electrons as well. So that gives us 8 total electrons. So we can then form our skeleton. So carbon in the middle, hydrogen on top, on the right-hand side, on the bottom, and on the left-hand side. So this is a Lewis structure. There aren't any lone pairs here. So that's 1, 2, 3, 4 bonding pairs. That's 8 electrons. Each one of these has, carbon has its 8 electrons, hydrogen has its 2 electrons in each. What ends up happening is that we see, so how do we then calculate the formal charge based on this? So carbon has its 4 valence electrons. It's the usual 4 electrons because it's in group 4A, right? So that's okay. Then, okay, so group 4A, so then minus 0. So it's the lone pair electrons. So there are no lone pair electrons because they're all in bonding. Plus a half of the 8 bonding electrons. So where did the 8 bonding electrons come from? So 2 from each of these. 1, 2, 3, 4 bonds. So that's 8 electrons from those because there's 2 electrons in each bond. So that's going to be 4 minus 4, which gives us a formal charge of 0. Okay. So here we can see that the different structures can have different formal charges. So carbon, again, group 4A, so it has 4 valence electrons to start with, minus 2 for the lone pair here, plus a half times 6, which is from the 3 bonding pairs here. That's 6 electrons, so a half times 6 is 3, so it's 4 minus 5 equals minus 1. So in carbon monoxide, which is this here, we have a formal charge of minus 1 on carbon. And then the oxygen here, it has a formal charge plus 1. So it is in group 6A, so it has 6 valence electrons, minus 2 for its lone pair, plus a half times 6 for the 6 electrons in the bonding pairs. And that gives us a plus 1. So it's 6 minus 2 plus 3. So it's 6 minus 5. So that equals plus 1. Okay. So the sum of the formal charges on the atoms in a molecule must be 0. So that was okay. Even though this was minus 1 and plus 1, that's fine because minus 1 plus 1 is 0. So the formal charges here should be 0. So the sum for the atoms in an ion equals the charge on the ion. So write the Lewis structure and determine the formal charge of HCN, HNC, which is the best way to represent hydrocyanic acid, and why. Okay, so it's not actually going to do this out for us. Okay, so let's turn up space here. So here, in both of them, we'll have the same number of electrons. So hydrogen will have 1 electron, carbon will have 4 valence electrons, and nitrogen will have 5. So that will give us 10 total for our valence electrons. So we have H, C, N, right? So so that's 2, 4, so that's 4. So it means we have 6 electrons remaining, because from each of these bond pairs, remember the bond pair has 2 electrons. So 2 times 2 is 4, 10 minus 4 is 6 remaining. They go on the nitrogen like so. Then what happens is we think about, so hydrogen has 2 electrons, it's happy. Carbon has 4, it's not happy. Nitrogen has 6, it's not. It is happy, or sorry, has 8. It is happy, but because carbon's not happy, what ends up happening is these lone pairs form triple bonds. So we have like this. Then for the HNC, we do the same thing. Of course, if we follow our Lewis rules, this structure won't be the one. So okay, so then we put our valence electrons here, because we put them on the ones outside. So okay, so then nitrogen again only has 4 electrons, so form a triple bond here like so. So nitrogen now has 8 electrons, and it's really happy. So get rid of these. Oh, not too far. Yeah, hang on, I'll fix that. Nitrogen again. Okay. So what are the formal charges here? This will help us to determine what is the best way to represent hydrocyanic acid. So the formal charge on hydrogen is, so the formal charge, remember, is Fc is equal to the valence, which I'll just call V, minus the sum of lone pairs plus a half of the bonding pairs. The bonding pairs divided by 2. Okay. All right. So the reason why the bonding pair is divided by 2 is because, remember, the electrons are shared between the 2 atoms. So the formal charge on the hydrogen here is the valence of hydrogen is 1 minus the lone pairs, there's none, plus a half of the bonding pairs. So the formal charge on oxygen here is 0, and 0 here for this oxygen as well. For carbon then, the central carbon, so it is, the valence of carbon is 4, and then it's going to be minus the number of lone pairs, of which there are 0, plus the bonding pairs divided by 2. So 1, 2, 3, 4 bonding pair electrons, so that's 8 electrons, divided by 2 is 4. So again, the formal charge here is 0. Then for this nitrogen, the valence is going to be 5 minus the lone pairs, which is 2, and the bonding pairs, which is 6 divided by 2 is 3. And so the formal charge here is 0. Okay. Here then for the second one, the nitrogen here has a valence of 5 minus 0 for the lone pairs plus 8. So there's 1, 2, 3, 4 bonding pairs. So it's 8 bonding pair electrons divided by 2, which is 4, which would give a formal charge of +1. And then for carbon, it is group 4. Okay, so it's got 4 valence minus 2 for the lone pair plus a half of the bonding pair. So there's 6 bonding pairs, or sorry, 3 bonding pairs. That gives us 6 electrons. 6 divided by 2. So that's going to be 2 plus 3 is 5. So that's going to give a -1 for the formal charge. So Anyone hazard a guess as to which one, in the first one or the second one? So is it going to be number 1 or is it going to be number 2, which is going to be the most stable? All right. And why is it going to be the most stable? All right. Good work, Zeke. Good work to everyone else. I'm sure most of you knew that, but if you didn't, that's okay. Don't worry, we'll get there. And if still doesn't seem clear, you can always talk to me, and we can try and look at more examples. So more on formal charges. So the sum of the formal charges on all the atoms in a molecule is 0, while for an ion it will be equal to the charge on the ion. In using the concept of formal charge, we should keep the following rules in mind. Using the most plausible Lewis structure is one with no formal charges, so formal charges of 0 on all atoms. Where formal charges are required, they should be as small as possible, and negative formal charges should appear on the most electronegative atoms. So, so formal charges on an atom, a molecule will be 0. So we saw that here. So even though this was the not this stable structure, it still was a molecule, because like the +1 here and the -1 here cancel out, and this was overall neutral. A molecule should be neutral overall, otherwise it would be an ion. And so that's kind of what that means. So usually the most plausible Lewis structure is the one with no formal charges of 0 on all atoms. So we want them to be as small as possible. Adjacent atoms in a structure should not carry formal charges of the same sign. So we shouldn't have positively charged, two positive formal charges beside each other. That shouldn't happen. Formal charges on the atoms in a Lewis structure must total to 0 for a molecule and to the net charge for a polyatomic ion. Oxidation numbers. These. So charges on bonded atoms are assigned by giving the more electronegative atom all the shared electrons, and such charge assignments are called oxidation numbers. We've seen this before. Whenever we talked about like iron 2 oxide and iron 3 oxide, like way back in module 2. So the ion charge, here we have electrons are transferred. So for example, sodium chloride, we have a transfer of electrons. Oxidation number, the electrons belong to the more electronegative atom. So in sodium chloride, sodium is in group 1A, so that generally indicates that it is going to be a lower electronegativity. And so the electron here, that was why the electron was transferred from the sodium to the chlorine. This chlorine has the electron affinity, if we recall, as well. Chlorine's electron affinity is quite good, and so it likes to have an extra electron. So in the formal charge, the electrons are shared equally. So we have sodium chloride, so Na plus, Cl minus. So overall, the formal charges will neutralize. Sure, why not? Resonance structures then. So this is like the same Lewis backbone, but different placement of electrons. So equivalent Lewis structures that are the same except for the placement of the electrons. So more than one Lewis structure. Adjacent, our structure contains double or triple bonds, and only one bond length exists. Bond length is shorter than a single bond, but not as short as a double or triple bond. And so resonance structures have the same arrangements of atoms, but different arrangements of electrons. And the structure, the actual structure of the molecule is a composite or hybrid of the equivalent resonance structures. So it's a lot of words. I really find it's easier to describe it in like a picture like this. So this is ozone, O3. So these are two Lewis structures for ozone. And what we end up with is like a system where two of the oxygens are double bonded and the other is singly bonded, but there's no real reason as to why one should be single and one should be double. So what ends up happening is that both are possible, and what we end up with is kind of an average structure. So the bond length here and here will be the same, as you can see here in the actual structure. Even though this is formally a double bond and this is formally a single bond. Because this double bond can be here or here, it sort of like flips between, like both can happen. And so it's longer than a single bond, but shorter than a double bond. Or sorry, shorter than a single bond, but longer than a double bond. That's right. And it just sort of, this is the idea of resonance. Like, so this double bond can be actually on this side, so it can go over here. That's fine. And then this would be a single bond. And then this can go back and we can form this structure again. These are interchangeable and the real structure becomes like an average. So we go back and forth between these. There's no particular rhyme or reason to which one is the more common. And so both become equally common. And we end up with a system which has an average bond length. We can have it for other things. If we recall earlier, we had this structure here. Like this. So actually this double bond can sometimes go up here onto the oxygen, and we can have like a single bond but a negatively charged. So this is obviously not the stable Lewis structure, but it is possible. And then this become positively charged, and then this. So really this one is the one that's most common, but it is possible for these electrons to go on the oxygen. And I think most of you will eventually do organic chemistry, and you will see something like that in organic chemistry. What is the Lewis structure of PO43 minus? Let's end it here on resonance. So I'll go over resonance one more time, and then we'll leave it there. So resonance structures, so equivalent Lewis structures that are the same except for the placement of electrons. So you have more than one Lewis structure, 2 Lewis structures here, right? So there we go. So that's our first part. Contains double or triple bonds. Yep, double bond. There we go. Only one bond length exists. Yep. So these bonds, even though they're formally double and single, they have the same length. Okay, so that's ticked off. So we had more than one Lewis structure. Yep. We had the structure contains double bonds or triple bonds. Yep. We had only one bond length. Yep. The bond length is shorter than a single bond, but not as short as a double or triple bond. Well, we don't really know that because we're not told what an oxygen-oxygen double bond length would be, but sure, why not? We'll assume that that's right too. Resonance structures have the same arrangement of atoms. So yep, oxygen, oxygen, oxygen. That didn't change. So okay, so that worked. And then the actual structure of the molecule is a composite or hybrid of the equivalent resonance structures. That's true as well, because even though this is a single bond and this is a double bond, we see and observe that they have the same bond length. So what does that mean? It means that there is a resonance structure existing here. And so the actual structure of the molecule is a composite, this being the actual structure, these being the resonance structures. Okay. All right. All right, so that was resonance structures. I'll try and make, well, I have a few topic videos on Lewis structures, so I'll post those this afternoon as well. It might be useful for explaining this in more detail for those of you who have a little bit of uncertainty regarding the exact procedures. Exceptions to the octet rule include molecules with an odd number of electrons. These are sort of so-called free radicals. These are an important class of chemical compound, which are very reactive, and they are useful in all sorts of organic chemistry transformations, such as nitrogen oxide, that is a free radical, or has a free radical. Molecules with less than an octet, such as BF3. So BF3 is a stable molecule, but yet whenever we draw it out, we see that the boron, the least electronegative atom, is surrounded by the fluorines, but there only are 3 of them, so it's only 3 bonds, and then that's only 6 electrons on the boron, but yet it still is a stable complex. Molecules with more than an octet. So this is only possible when the valence shell is greater, n is greater than 3, so d orbitals are able to accommodate extra electrons. So whenever we start to get further down the periodic table, some very strange, well, not very strange, but we can explain it, but some unusual behavior starts to creep in. Things like PCl5, P is in the same group as oxygen, but yet you couldn't imagine oxygen doing something like this. Oh, sorry, it's not, it's in nitrogen, I always get that. So it's nitrogen, for example, forms compounds such as NH3. These are both in group 5A, but it's because of the extra size of the orbitals that sometimes things like this can happen. And then SF6, that's got 6 bonds to the central sulfur. Sulfur is below oxygen, it's in group 6A. So strange things can happen. And it's because of the availability of those d orbitals. They might not have electrons in them, but they might be able to accept electrons. So here are some Lewis structures for hypervalent compounds in which the central atom exceeds the octet. So we have some from group 4, group 5, group 6, group 7, and group 8. So in group 4A, we can have silicon pentafluoride. So it's got a negative charge. So it's a silicon atom in the center, and it's got 5 bonds this time. And that's because it's got this availability of a d orbital. And so that means we have what's called an extended octet. So what we can have is more than 8 electrons surrounding the silicon. But remember, we've always got to keep and make sure that we're accounting for all of our electrons and all of our charges. And so that's why this one is silicon pentafluoride. Here we have silicon hexafluoride, which is 2 minus. And here we have 6 fluorines. Now, you couldn't do this, for example, with chloride because chlorine, and it's much, much larger than fluorine. Remember that as we go down the periodic table, atomic sizes increase. And so one of the reasons why fluorine is capable of doing these structures that we see here from groups 4 to 8 is that it is very small. And so it's capable of fitting around the central atom. So that's another thing you have to consider is like in the first row of the periodic table, you know, nitrogen, oxygen, fluorine, they're quite small, at least compared to the next row and the rows after that. And if something can't fit, then it's not going to be able to bond. And if it's not able to bond, then it won't form that shape or that molecule. PF5, so in this case, phosphorus is quite large, at least compared to nitrogen. And so what's going to happen is additional space is found around the atom, which can host these 5 fluorine bonds. You can also get it done with PCl5. That's also very common. Phosphorus is well known for having up to 5 bonds, and so that's because of this availability of these d orbitals, 3d orbitals in this case, which are not available to, for example, nitrogen, which is also in group 5A. In group 6A, then that's things like oxygen, sulfur. So we have here SF4 and SF6. So we have sulfur forming 4 bonds, but having a lone pair of electrons. And then we have SF6, we have sulfur with 6 bonds. These are quite well-known sort of phenomena. You'll see, especially this SF4 as an example of of a certain type of molecular shape. Quite often SF6, obviously we know a lot of these sorts of 6 bonds to a central atom, at least in transition metals. So group 7 anything, you can also have, for example, fluorine cannot form these extended octets because usually what happens is that it's a halogen, such as chlorine, and then the one above it, which is fluorine, or bromine, which can also be fluorine or chlorine. It can form these sorts of extended octets, these compounds in which the central atom has more than 8 valence electrons. And then group 8, xenon, pretty much the only one which is really reactive of the group 8 elements. It can form compounds with fluorine. And so here we have them. So we usually talk about group 8 as being the noble elements, about those being really stable, not really wanting to react or form any sort of molecular compounds, but in fact, things like xenon do. And so they are capable of forming these compounds with more than 8 valence electrons. Molecular shape, why is it important? Well, it sort of has a lot of implications for the way that molecules can fit into different places. And why is that important? Well, it's especially important in things like medicines and in things like reactivity, because things like this is a drug. This is a platinum drug. If it is the cis variant, if it is cisplatin, it is one of the most widely used anti-cancer drugs for cancers which are not resistant to platinum. So cisplatin is a potent anti-tumor agent. So it is very important in our fight against various strains of cancer. Now, not all cancers are treatable with cisplatin, but many are. And if it wasn't for this medicine, many lives would not be saved. However, if it is a different shape, so cis and trans, we'll see in a moment, relate to the ways in which the chlorine and the ammonia, remember the NH3 is ammonia, are arranged around this central platinum. And so if it is the cis orientation, then it is a very nice medicine. But if it is the trans orientation, it has the same sort of compound formula, molecular formula. Both of these cis and platinum have the same 1 platinum, 2 chlorines, and 3 ammonias, but the trans variant, so it's slightly different shape, is toxic. So, and it's not a medicine. And so you can see that it's kind of like molecular shape starts to be important when if we think about putting certain medicines into our body. If it's not the correct shape, maybe it has an adverse effect. Maybe it is in fact toxic. But if it has the correct shape, then it can be very beneficial. So the only difference here is the molecular shape. And this affects the physical properties of it, affects the chemical properties, and so on. So here we have cis and trans retinol. So this shape transition is one of the ways in which our eyes are able to perceive light. So this sort of chemical change or physical change happens whenever our light enters our eye. So we have here what's called cis retinol, where the 2 major groups, this part and this part, are on the same side of a double bond. Remember we talked before about a carbon-carbon double bond. We talked about it briefly. You'll talk a lot about it in organic chemistry when you do that. But carbon-carbon double bond. So this is the cis version where if I call this part here R1, and I call this part here R2, just to make it easier, then I have R2 on this side and R1. So I have, this is the cis version. Now there are also hydrogens on this side. Don't forget those. So this is the cis version. And so this interconverts with the trans version, which, let's see, looks a little bit like this, where R1 is now on the top and is now opposite to R2. and we call this the transversion. And so it's this change, this sort of movement or flipping of the bond, which enables us to sort of perceive, well, an electrical response happens inside of our eye, and we perceive that as seeing the light. So cisretinal becomes transretinal, so a different shape due to the light triggering a signal that is ultimately interpreted by the brain as I see the light. So our brain goes, oh, the light is bright now. So the energy from light is what causes this flip to happen. So remember we learned about the electromagnetic spectrum before. So this is an application of some of that light that comes into our eye, and it sends off an electrical signal, which is triggers something in our brain and says, oh, the light is bright here. And it is this sort of flipping of the structure from cis to trans retinal. So cis groups, the major or heavier parts of the molecule are on the same side, and trans, they are on opposite sides. Molecular shapes. Lewis structures tell us how atoms are bonded in a molecule, such as bond pairs and lone pairs, etc., but they don't actually tell us what the shape is, because we're drawing it on a flat piece of paper. So if we drew methane, CH4, we drew it as this sort of structure, where there was a 90-degree angle between each of the carbon-hydrogen bonds. And this would indicate to us that, in fact, CH4 is going to be flat. So the Lewis structure suggests that HCH bond angles are 90 degrees and that the molecule is flat. Now, this is not actually true. Molecules exist in three-dimensional space. We saw that whenever we talked about the atom, that the electrons exist in a sort of sphere around the central atom. So molecular shapes. Experimentally, however, the HCH bond angles are found to be 109.5 degrees. If this is the case, the molecule cannot be planar, because if we have these 109.5 degrees, if we try to fit those in a planar structure, this is a planar structure, each HCH bond is 90 degrees from each other. That totals 360 degrees. Now, we're told experimentally that this bond angle, this HCH bond angle, is in fact 109.5 degrees. So how do we rationalize that? If we do 109.5 degrees and multiply that by 4, we get a much larger number, a larger sum. So it's greater than 360 degrees. It basically means that we have to orientate these atoms and these bonds in a three-dimensional shape as opposed to a two-dimensional shape in order to gain access to this additional degrees of freedom. And so the methane molecule must be 3D, since the sum of the angles is greater than 360 degrees. So in order to fit everything in, because if we just went around in a circle on the page, that's 360 degrees. So then we have to come back around again and for another, 78 degrees. So that means we would have overlapping of the different bond angles, which would not be appropriate for our structure, because we have like this extra 78 degrees that are in the 438 degrees. So in order to accommodate these bond angles, the 109.5 degree bond angles, the atoms adopt a new 3D geometry to minimize the repulsion between the atoms. So this planar structure that we got from the Lewis structure, which is still very valid, and it helps us to look at the connectivity of the molecule, in fact becomes this sort of three-dimensional structure here, where we have two of the hydrogens are in the plane of the page, but then one is going in towards the page and one is coming out towards us. So we have like this kind of three-dimensional shape. Whenever we have an arrow like this, which is filled in, this arrow, then that means it's coming out towards us. So it's towards us, out of the page. and then this sort of dashed line, or sometimes you see it like sort of like this, like a dashed wedge. That means it's going away from you. So the molecular geometry of CH4 is said to be tetrahedral. The hydrogen atoms fit at the corners of a regular tetrahedron shape with the carbon at the center. So a tetrahedron is something like this. Hang on, I'll remove that old one. Where's the eraser? Something like that is a tetrahedron. Okay. So molecular shapes. In order to predict molecular shape, we assume the valence electrons of each atom in the molecule repel one another. So if we think about that, they're negatively charged. So there's going to be some repulsion between negative charges. They don't like to be near each other so much. So one of the driving forces here is this repulsion. So in order to predict molecular shape, we assume the valence electrons of each atom in the molecule repel one another. When this happens, the molecule adopts a 3D geometry that minimizes this repulsion, where lone pair repulsion is greater than lone pair bond pair, which is greater than bond pair repulsion. And so this process is known as VSEPR, valence shell electron pair repulsion theory. And so this is an important theory in just trying to sort of rationalize the structures of many well-known geometries and molecules. So what we have is this idea that those electrons which are sort of extra, the lone pairs, their repulsion from each other is much greater than whenever we have lone pair bond pair repulsion. Bond pairs, remember, are those that are shared between different atoms in order to form bonds, which is greater than bond pair repulsion. So we can sort of think about, well, why is this? Well, if we imagine that the bond pair electrons are actually held sort of in between two atoms, then this means that they're not totally focused on one atom. And so they're going to be less likely to repel each other. Like they're more caught up in the bonding, and so they don't have this sort of lateral movement to repel. Molecular shape sense. So valence shell electron pair repulsion. A molecule can be described in terms of the distribution of the bonding atoms about the central atom. And so this leads to something called molecular geometry. Molecule can be described in terms of the distribution of the bonding pair electrons, BP, and lone pair electrons, LP, about the central atom. And so this is electron pair geometry. So usually the first thing we kind of do is we distribute the electrons across the sphere which makes up the central atom. And then we work out around that. So here we have electron pair geometries and how they translate into different structures. So here we have two pairs of electrons. You have a linear shape. We can draw this out like this. So here we have 180 degrees between our two bonds. We have a central bond here, and we have two atoms attached to that. One of our types of notation is this AXE notation, which we'll talk about in more detail. But A is the central atom. So in this case, here, this white one, and then X is the atoms which are bonded to a linear shape, 180 degrees between the two bond pairs. Then trigonal planar. So we have three pairs of electrons, three bonds. The actual atoms, in this case, BF3 is an example. We end up with A and X. So we have AX3. Okay, so yeah, so I'll go back to trigonal once more. So the reason why it's called trigonal is because it has this sort of triangular shape. If we draw a polygon around its a sort of atoms furthermost from the central atom. So this sort of black dot here, it indicates that that's the central atom's position. So here we have 3 bonds. We have A in the middle from our AX notation. We have, and then we label the outer atoms as X. So we have AX. So here we have AX3. An example of that is PF3. And so we have 3 pairs of electrons here. Tetrahedral then, so that's like our CH4 or CF4. So that's got AX4. So A is the central atom, X is the atom or the atoms bonded to that. Tetrahedral because of the shape that it adopts, like this, the polygon. 4 pairs of electrons. Here we have trigonal bipyramidal. So we're starting to get slightly more complex. We have A in the middle again, and then X on the outside. And we have 2 types of bond angles now, though. So previously with linear, it was 180 degrees. Trigonal planar, it was 120 degrees. Tetrahedral, it was 109.5 degrees. Now we have 2 different types. I forgot to mention also, like the tetrahedral is where we start to move into 3-dimensional shapes, or truly three-dimensional shapes. Trigonal bipyramidal then, so it's got 2 tetrahedrals sort of attached to each other. One on top, one on the bottom. So an example of this is PF5. We have 120 degrees amongst those which are in a plane here, a triangle shape on here, and then 90 degrees between those that are above and below this sort of triangle. See the triangle here, like that. And so we have 2, this one and this one, which are above and below that triangle. So that's how you can kind of see the triangle here in the polygon. And then octahedral, this is a very important structure. It has 6 pairs of electrons. An example is AX6, such as SF6. So we have A in the middle again, as always, and then we have the X groups here. Like that. So octahedral shapes then have a polygon that looks like this. It's an 8-sided polygon. So these are central atoms surrounded only by single bond pairs. So each one of these bonds, these AX bonds, is a single bond. There are no double bonds in this instance. And we also don't have lone pairs involved here. So that means that we can use our AX notation, where the A is the central atom, X is one of the atoms bonded to it. So we have AX2 for linear, AX3 for trigonal planar, AX4 for tetrahedral, AX5 for trigonal bipyramidal, and AX6 for octahedral. Electron domains then, so regions where it is most probable to find pairs of electrons. So these can be bonding pairs. So electron domains could be here. This could be an electron domain for our trigonal planar structure because that's where the bond pair is. The bond pair will be between A and X. So bonding pairs, electron domain. So single, double, and triple bonds all represent just one domain. So even if you have more than a pair of electrons, it's still only one electron domain. Non-bonding pairs then are also an electron domain. So this is things like our LPs. Geometry then is also affected by this lone electron domain geometry. So remember that we mentioned not way back, but a few slides ago that lone pair repulsion is stronger than lone pair bond pair, which is stronger than bond pair repulsion. So lone pair is stronger than lone pair bond pair, which is stronger than bond pair repulsion. And so the previous molecular geometries that we were looking at, these ones, they didn't take into account lone pairs. Thankfully, none of these examples had lone pairs, so it turned out to not be such a big problem. But what if we had lone pairs? We're just dealing with bond pair repulsions in each one of these, so that's something we missed. So that's why we don't really use molecular geometry so much, and we look more at electron domain geometry. Because we can use, those bond pairs are still electron domains, and so they can still be utilized in this kind of geometry. If we don't have lone pairs, that's okay, but we still have those electron domains, which can give us the structures. So the arrangement of electron pairs in space is the electron domain geometry. The molecular geometry is then the arrangement of atoms in space. And so the molecular geometry is the one that we use to describe the shape, but it's the shape of the molecular geometry is influenced heavily by the electron domain geometry, which we will see shortly. So you can do some of this with balloons. Actually, if you're very good at blowing these balloon shapes, you can some molecular structures. So, for example, you can make linear ones like this, trigonal, planar, tetrahedral. Like the balloons, because of their rounded ends, will actually kind of adopt those geometries, just because it sort of minimizes the repulsion that is felt at these sort of central points. So it's the interface between the two, or between the balloons, which causes their shape. So here we just have two of them. So the furthest apart they can be is just a line. Trigonal planar, then they distribute equally 120 degrees from each other. Then if we have four attached here in the middle, they go to 109.5 degrees to form this tetrahedral shape. Trigonal bipyramidal, if you try to tie 5 ends together, you get a structure like this. And then 6 ends, you get a structure like this, which is octahedral. So it's trying to distribute the balloons in such a way as to sort of minimize the repulsion between them. And if you try to, like, for example, bend this one over here, like so, so that it becomes more like this here, what will actually happen is that it will bounce back to the original position.